Okay, so we're going to talk about primes, divisibility, etc. And what we're starting off is kind of the new exploration to number theory, building up to public key cryptography, which will be interesting to any of you who are computer science and interested in security. So primes and so let's go back to fourth grade. If I were to ask you what is 43 divided by 6? Well, before you guys learn how to use the fractions for this, you would say that is 7 remainder 1. So a more general idea for this, that's the same thing as saying that 43 is equal to 6 times 7 plus 1. A more general idea for this is if we have integers a, b, and c, and z. Actually, I'll write it like this. If we have integers a and b, then, no, a, b, and c, yeah. If we have integers a, b, and c, then we can write b is equal to ac plus r, where r is between 0 and a. So in this case, c corresponds to our 7, 1 corresponds to our r, a corresponds to our 6, and b corresponds to our 43. So that's all that's going on right now. We say that b is divisible by a, or a divides b. So in this case, we would have something like 6 divides 42. If r is equal to 0. So basically just if our remainder is 0, then we have strict divisibility and things play nicely. So here's a quick question that I'll run through, or two-part question that I'll run through to show you guys. So if a divides b and b divides c, then a divides c. So if a divides b, then b is equal to a times d. And then because it divides, because a divides b, that means that the remainder is equal to 0, so that's fine. And if b divides c, then c is equal to b times, let's call it f, which by substitution up here, then we get a df. Therefore, this guy right here is an integer, right? So we have that c is equal to a times an integer. Therefore, a divides c. So I'll change that to because a divides b and b divides c. We have that. Okay. So then the next one is if a divides b, and a divides c, then a divides b plus c, and a divides b minus c. So a divides b and a divides c, therefore b is equal to a times d, and c is equal to a times f. Therefore, b plus c is equal to a times d plus a times f is equal to a times d plus f, which is still an integer. So this checks out. And it's going to be basically the exact same idea for b minus c. So the next concept that we want to talk about is prime numbers. So if we have z greater than 1, 1 is not a prime number. For our purposes, you can just take that as a flat out fact. But the reason has to do with kind of higher algebra. So you'll actually see kind of why later when we talk about the cryptography stuff. But so if we have an integer greater than 1, then a number z and z greater than 1 is prime if its only factors, positive factors, or divisors are one-ended stuff. So note 1 not prime. So how do we tell if a number is prime? Well, there are a lot of different tests for it, but the simplest, old-fashioned one is just line up every single number, and you pick out the first number so we're not looking at 1, so we can cross that guy out. And then we pick out 2. 2 is nothing's been done to 2 so far, so we say yay, check, and then we cross out every single multiple of 2. So I'm just going to go straight down here, straight down here, straight down here. 2 is the easiest guy to do this with. So now I can go on to my next one. 3, that's prime because it's still unchecked. So that means that it's not divisible by anything that I've crossed out beforehand, and it can't be divisible by a number that's greater than it. So that's good. So 9 goes, 15 goes, 18 would go, 21 goes, 24 would go. Here, I'll still do that extra cross. But obviously it's unnecessary to do the ones that have already been done. 48, 51, 54, and 60. I'll just leave it at 60. 5, check. And 5 again, it's easy. It's just the things that end in 5 and 0. So 7, that's also prime. So now I would go through and eliminate all of the multiples of 7, which everything should be good except for 49. So, and now I would go through, check 11, check everything that I said I was going to do up to 60. Everything's already been crossed out. It's going to be the same thing for this guy, 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 but you should still go through and cross out everything. It's just all of them, them times all of the lower primes is already done. So rather than waste your time, I'm just going to circle up all of these primes. So that is the simplest algorithm for finding and listing primes. But nowadays with computers, we have better systems to find them. Also, another classic theorem that when it comes to prime numbers, which I think I actually already gave you guys at some point, is there are infinitely many primes. So this is the classic is a proof by contradiction. So assume for contradiction. There are finitely many. Which we can list off as P1, P2, P3, all the way up to PK. So PK is our last one. Therefore, we can look at examine P1 times P2 times PK plus 1. We can also think of this as pi equals 1 to k of pi plus 1. It's a slightly more efficient way of writing it. But this guy is not divisible by pi for any pi. Therefore, it would be prime. So, therefore, no finite list contains all prime numbers. I.e., there are infinitely many primes. Another interesting question. So people for millennia have been interested in the question of the distribution of primes and the frequency of primes, just kind of because they're interesting for in and of itself. More recently, we've had with the dawn of computers, we've had actual applications, but so this guy P of n is the number of primes less than n or equal to n. And this is roughly equal to n divided by the natural log of n. So the number of primes is roughly equal to your number divided by the natural log of that number. And this is a good estimate, but it is very hard to prove, so we won't bother with that. The next statement that is probably important for you guys to know is that for the integers, and we can very easily reword this for all of the integers, but we're only going to care about the positive integers. So I'm just going to have to focus on the positive integers. Every number has a prime factorization, has a unique prime factorization. So this guy right here, the unique prime factorization, uh, this might sound pretty trivial to you, that any system that would have some notion of prime factorization, sort of like not the rational numbers, um, would obviously have it, uh, but that's actually not the case. So if you look up Gaussian integers, so they look like a plus b root 5, a and b are integers, you will see that actually no, not everything has a unique prime factorization. That you can get things through several different ways, or through several different prime factorizations. So both of these guys are in the integers. Okay, so let's go about the proof and assume we have the smallest n such that n has two prime factorizations. It's pretty easy to see that a prime factorization will exist, because either it's prime or it's composite. But so we're just going to try to show the uniqueness here. So assume we have n such that n is the smallest, therefore n is equal to p1 times all the way through pk, and that's equal to q1 times all the way up to qm, we'll say. So let P1 be the smallest factor for either of these guys. So among our P's and our Q's. So we know that P1 cannot divide any Qi, because if it did, then we could just divide everything by Pi, then n divided by Pi would be, or by P1, would be a smaller number without unique factorization. Right? So now we can see, so now, therefore, Qi is going to be equal to, we'll call it Ri plus P1 times Ai. So each of our Qi's can be written like this. Therefore, n is equal to the product of these guys. So P1 A1 plus R1 times P1 A2 plus R2 all the way up to P1 AM plus RM. Right. So we can write this as P1 times, we'll call this T plus R1 times R2 times all the way till I get to Rm. Okay, so reminder, so Ri is strictly greater than 0 and less than P1. So this guy I'm going to call n prime. So we've got this new guy n prime. And this right here is going to represent something that can be turned into a prime factorization, right? So n prime is equal to R1 Rm, but it's also equal to Q1 minus, what do we call this? We called it, so I can rewrite R I is equal to Qi minus AI P1. So that's what I'm going to write all of these guys as. AI P1 all the way up to Rm is going to be Qm minus AM P1. Should be a 1 here. So if I multiply these guys out, I'm going to get that's equal to Q1 through Qm. So that all of these first terms, when I multiply them out, plus P1 times something we'll call V. So P1 times some integer V. I'm just pulling out all those P1s because all of them, except for these Lie terms, have a P1. Except this Lie term also does have one, because this guy is equal to n, which is equal to P1 times all the way up to Pk. So that means that this whole setup here is equal to P1 times U, if I just add V plus P2 through Pk. So that checks out right there. That but that tells me that there are, in fact, two different prime factorizations. Sorry, this should have been prime this whole time. So that tells me that there are, in fact, two different prime factorizations for n prime, because I have this one, which cannot have any p1s, and this one, which has p1s. Therefore, there exist two prime factorizations for n prime. Therefore, n is not the smallest. Right? Because we assumed that n was the smallest. Therefore, it must be unique. Prime factorization. And I encourage you guys to check out the Gaussian integers, as I said, that they'll be just kind of an interesting exemption to the rules as you normally think of them.